start again. We are discussing about VAE. It's one kind of autoencoder. That means it is basically used to shorten the data of image or anything. Let's say we have an image of 4 by 84, and we want to represent it by a Z vector, hidden vector, which is the size of let's say 32 or 64. So from this hidden vector we can reconstruct our original image, but it would not be exactly same, but most of the features would be there in the new image. So some idea of VAE is like say last time we were talking about a prior distribution. Like say we want to choose a prior distribution. So why do we need that prior distribution? Like say I have a hidden variable z, and from that I can derive x. So that means the hidden variable as a probability distribution that can generate x. But in reality we have only access to x. That means we know the distribution of we know the value of x. So that means we want to calculate the opposite probability of z given x. So how can we calculate this? Like say if we apply probability distribution probability formula, that means we have a distribution of z and z given x and divided by probability of x. So how can we calculate this in denominator part? So we can do that by like say taking all different possible value of z. That means summing over, like say taking the summation of all possible so we'll try to get all possible values of z, and by taking integration over that we can calculate this denominator part. But there are infinite number of values of z we can have. So that means we cannot actually calculate this value. It's intractable. So there is a way that is done is, like say, instead of calculating this p, we want to get a approximation function which is like say q z given x. So this approximator will work similarly as like p, and it will have some parameters that we can change, and it will behave same as like p, but it will not be the exactly same. So the idea of taking this approximation is that this is tractable. That means we can actually calculate this value, calculate this function, but not p. So that's why as we are trying to use q as an approximation, we need to find a way to find the similarity between these two distributions. So to find this distribution similarity, we need to get KL divergence. That means we want to minimize the KL divergence between these two distributions. If you can ensure that the divergence will be minimized, then we can use the q as the approximator of p. So that means we want to minimize the KL divergence between p of z given x and p of q of z given x. So but it's proven that if you want to calculate the divergence, minimum divergence, is equivalent to maximizing the another value, which is That means if you want to minimize the KL divergence between these two distribution, it's equivalent to maximizing these two terms. That means it basically means the likelihood of reconstructing the same data. That means log likelihood. That means given Z, which is the output of encoder, what is the likelihood that we would be able to calculate X? That means this is a likelihood loss, and this is the KL divergence between true distribution of Z. What is the exact distribution of Z, which is basically a prior distribution, and the approximate distribution, which we have just defined. That means we don't need to find the exact P. We just need to find the distribution of P with Q, KL divergence. That means now if we want to build our like say,
Shante, so how the minimizing KL divergence between P G given X and Q G given X leads to the...
I mean, it's a very long mathematical proof. I don't understand.
Okay.
So it's like say, there is a proof. There is one guy, he proved that it's minimizing this one is actually equivalent to this one, but I don't know the exact proof.
Okay. So I think yeah, that one day we need to study probabilistic generative method. So the variational inference and things like that. It might require a separate seminar about how we can drive that part. How many people in this room have heard about the KL divergence?
Very big understanding.
Okay, and entropy, information theory? Yeah. And the graph probabilistic, the Bayesian, we know the naive Bayes, right? However, there are more complex version of the Bayes that uses graph to model, to represent the dependence relationship. So things like that. We have a given G, we generate X, things like that. So I think at some point we need to tackle those mathematical foundations. I checked it myself. It looks like it requires heavy math. So I'll start studying it myself, and one day I will do that seminar. Okay. Okay. Let's continue.
So from here, if we want to build the network, it will like say input will be X, then the encoder will be just Q, which is so it will find output of Z given X. So encoder will output Z. From here, the decoder part will be given Z, will find P, will find the X. So probability of X given Z. So this will be the basically two network, one for encoder and one for decoder. So the output would be basically X bar. So if X bar could be same as X, or sometimes it could be different. So now the problem is the encoder actually directly does not give you the Z. It gives you mu and standard deviation. So if you have a like say from that mu and variation, we can sample. But if you have a sampling in our network, actually we cannot draw gradient descent. So we have to somehow make this sampling as a way to do gradient descent. So to do gradient descent, there is a technique which is called parameterization. That means converting this random node to a deterministic node. So deterministic node, if you have a deterministic node, we can do like say back propagation. So by just having a sampling, we cannot do back propagation. So to do that back propagation, so there is a so we have like say mu standard deviation, and so what we will do, we'll from standard normal Gaussian, like say 0 mean 1 standard deviation, we'll find a value. So from that value we'll calculate a deterministic node which would be z. So z would be mu plus standard deviation times epsilon. So that basically means we are basically converting this random value from our sample to a deterministic value z. So if you have z, then we can pass this z to our decoder. So decoder will produce output. So if you have output, then we can do differentiation, like say d of a given dz. So if you have dz, then we can go back to here, which is dz given del mu. So also we can do for standard deviation d of z given d of standard deviation. So in this way we can go backward and see how much value is changed due to this mu and standard deviation. So this is the way to do of reparameterization. So there are basically these two costs associated with the loss function. One is reconstruction cost and another is KL divergence cost. So if we have like say only like say if we have only a KL divergence in our cost function, like say we don't have any reconstruction loss, what will happen? So in that case, so if you have only like say reconstruction KL divergence, like so we have image data, handwritten image data 0, 1 to 9. So in case of only KL divergence, what will happen, like say in our z vector dimension, like say we have the 2D dimension. So like say this is the data point for 2, this is another data point for 2, and this is one data point for 1 data point for 1. That means there is no cluster between the points in our original input. That means we cannot cluster the similar data points together. But if we use only like say reconstruction loss, we'll have just one like say 1 in this region, then 2 in this region, 3 and another region, but there will be a gap in between. if you use only like say a reconstruction loss. But if you use only KL divergence, that means all the data points will be like say coming together. There will be no space, but we cannot like say cluster. We cannot like say classify the points. We cannot divide the points into separate regions. Like so we cannot say that this portion is only for digit 0, this portion is only for digit 1. We cannot say that if we use only KL divergence. So we need both this loss and KL divergence, such that all the points would be coming together at the same time. They can be clustered. Like say, if we by sampling, if we choose a point from here, we can check. We can use this point for like say digit 0. From sampling, if we choose a point from here, we can define that this point is coming for digit 6. So this way we can from this sampling space we can reconstruct our original image. So that's why we need this.
I have a question. So how we can get expectation of, for example, log px given z in the neural net? Let's say we get an image x and we generate some g, and then how we can get the px given z?
This is basically our decoder part. So when you get z, we'll pass that to our decoder network. Decoder will produce basically x, x bar. So then we'll check how much x bar is similar to x. That means it's basically difference. That means from z we'll get x bar. Then we'll check what is the probability that we have got x.
So let's say we have a two image.
Yeah.
Then how we can get the?
Like say I think it is done by like say a check for individual pixel value. Like say in our original image I have 64 by 64 dimension. Each value is 0 or 1. So in our output we will also have same thing. Then for each individual pixel we'll check whether they are matching. From their matching pixel,
but
we'll
they
take
are like a floating continuous number. So let's say the pixel value is continuous. Then how we can?
No, I don't. Pixel value is continuous. In that case, they're done. It's done by taking difference. Taking difference and then. So how much they are close to each other for each individual pixel point.
Can you write a formula? It must be used in the source code, right?
Yeah, but it's done basically in neural network. There is a function log probability. So by using log probability, like say you have two different data points, x and x bar. So and
I thought we use the mean squared error between the original image and the reconstructed image.
So there is a mean square error. Then what will be the denominator? Will there be any denominator or not?
No, I don't think so. But I don't know how that expectation works. But
How?
I don't know how that expectation works. But from what I remember from the code, it is just the mean square error between the original and the output.
I think the expectation is getting a reduced mean of the log probability. So let's say we have 1,000 data, then we get the mean of those 1,000. That's how we get the expectation. Okay, then how we can calculate the KL divergence between Q and P? Q Oh.
KL divergence.
In the neural net. So we have in neural net how we can calculate that.
I mean, there is already built-in function to find the KL divergence. So basically, KL divergence, the intuitive idea, like say, like say I have a distribution which follows a normal distribution. Like say for each index I have some values. Now if I want to approximate this distribution with like say uniform distribution, like say we want to set the uniform value for each data point. That means there is a difference.
No. I mean in the autoencoder. So what is the QG given X? Is the
in the source code?
Yeah.
So this is basically the encoder part.
Yeah,
That means
so
output
it gives
of
the latent factor. And how we can get the PG?
PG is just our Gaussian distribution, which is zero mean and 1 standard deviation. So it is basically fixed.
So my question is, the Q G given X is decoder
Encoder output.
encoder output. Then we have a normal distribution.
Yeah.
Then how we can get the KL divergence?
That means like say like so we have z dimension of 32. That means from sampling
So from the mu and sigma.
yeah, from the mu and sigma we will get like say z value,
Z value.
deterministic node.
That is the Q X given G, G given X, right? So let's say the neural net output generates mu and sigma,
Yeah.
okay, and we sampled from it.
Yeah.
Is that Q G given X?
Yes.
Okay, so we have
And also this is independent. That means it basically means a distribution. That means this is a distribution of zero mean of 1 standard deviation. I mean this distribution is fixed. Then we want to check how much this distribution is similar to our normal distribution. That means this is fixed. We don't need to calculate any value for this. Then our next step is how much this Q is similar to our normal distribution.
I cannot understand it because I ignorant. So please bear with me. For example, in Q we have a mu and sigma, right?
Yes.
So we have a mu and sigma for 32 values. So and those are Gaussian normal distribution,
Yes.
which is a mean of 0
Yeah.
and standard deviation of 1. So does that mean then the mu and sigma should be 0 and 1 in the Q?
Yeah. It means
It's a trivial then. Just use a trivial, isn't it?
But you see, this mu and sigma is not.
It generates from the neural network.
Yeah, neural network. It's not always 0 and this is not always 1. These two, I mean, this is coming from neural network, so there is no guarantee that this mu would be 0. There is also no guarantee that this sigma would be 1.
Okay.
So that's why we need to find the divergence. That means how much, if it is actually producing 0 and 1 standard deviation, ultimately the divergence would be 0.
Can you show the source code part of calculating KL divergence?
Okay, so we can now code.
Just show me the code segment and explain.
Sanjay, can you repeat? PG. So this is the divergence. So it's finding divergence between posterior and prior. So posterior is coming from encoder and prior is the Gaussian distribution, which is coming from here. That means 0 mean and 1 standard deviation. So we are trying to find how much posterior is same as prior.
Posterior, can you show me make encoder function?
So it's taking the image data, then it passing through a dense network. From the dense network, it's producing mu, and scale means deviation, standard deviation.
Okay. Okay, I think.
So now, then it's trying to check how much these two are similar.
Okay, I see. Yeah. Okay.
So now we can finish our unfinished code.
Ruben, we need a laptop in the seminar. We usually try to do live coding during the seminar, okay?
So last time we make created function for encoder, decoder, prior, and also defined the loss function. So which is the same as this one. Means likelihood minus divergence.
Hello?
Hello?
Hi, 18 and Center with a reminder call that I had an appointment tomorrow with Dr. Lewis at 9.
Actually, I'm the automatic reminder call and I texted it.
So now we'll do training for MNIST data.
Bye. Shade, can you check the TensorFlow KL divergence function and how they calculate the KL divergence? Okay?
Okay. I can check now.
No.
Yeah.
After this
Okay.
seminar, and send me a Slack. Send a Slack to general channel about how given two Gaussian distribution, TF KL divergence function works.
Okay.
Okay.
So there are 10,000 images of MNIST data as a test data. So we'll use that to calculate, to test our neural network. So we are getting value of loss function and ports, which is the output from encoder. Also some samples. Like so we'll test for like say 10 samples, and we'll check the decoder output. That means one part of our network is to generate image. That means we'll sample from Gaussian distribution, then we'll check how much it can generate our original input. That means this is the sample part. That means this z vector, actually now we are not getting this z vector from encoder. We'll just generate from our Gaussian distribution. Like say 10 samples, then we'll directly pass to the decoder, and we'll check whether it's learning.
Focus in in range.
What was the elbow again?
What do you say?
What was the elbow again?
Evidence.
Elbow is the loss function.
Evidence lower bound.
Evidence lower bound.
Yeah, it's a variational lower bound is variational low bound is I forgot the formula, but evidence law simply means we use the sample mean to get the variational low bound.
Okay.
Then we'll also plot our codes. Then we also plot images which we have sampled from standard Gaussian. So there are total 60,000 training images in MNIST. So in each batch we will pass 100 images. Now we'll write the function for plotting.
In the make decoder function, what is the TFD that independent function? Make decoder function, decoder. Yeah.
So independent function is a collection of multiple distribution.
Okay.
Like say that means in our image each pixel represents one distribution, which is a binary distribution. That means whether it would be 0 or 1. So this 2 dimension means the width inner 2 dimension, which is 28 by 28. So it means this 2 dimension belongs to the same point, one particular point. So what it does, like say instead of producing binary distribution for each individual pixel, this independent distribution will give you the distribution of whole image. Like say whether what is the output of each individual pixel.
Code is latent vector, right?
Yes.
Code is latent vector and data shape is 28 by 28 and
So these 2 is basically used for these last 2 dimensions. That means 28 by 28, which basically means one image. So this independent will give you the distribution for each image.
What do you mean by distribution for each image?
That means, like, so whether each pixel value would be 0 or 1. In our case, it's a gray image. That means whether it would be 0 or 1.
So, let's say the code is, let's say, what's the dimension of the code?
Code is 10 by 2.
10 by 2?
Yes, like say 10 means like say we are passing x images, so it would be x by 2. Like say n images, n by 2. This would be the dimension.
You mean code? Ah, okay, so the latent vector dimension is 2, right?
Yeah. So we are setting is 2 because we want to plot it on our graph.
So, given, if I understand decoder is given 2 number, generator image,
Yes.
which is a 28 by 28.
Yes.
So I thought make decoder function is returning given code, return the image.
Yeah, that's the ultimate target. Like say, decoder will produce the same output as like the input dimension. So from the independent image, I mean that's not the end of it. Ultimately, from decoder we have to do sampling. Like say from here we have to taking mean. Yeah, I mean we need to take mean. I mean independent distribution is not actually giving me any value. Ultimately, from here we need to take mean to get the actual samples.
So, given n by 2, let's say if we think about n is 1,
Okay.
we just got the
Yes.
one code,
Okay.
and it will return 28 by 28 continuous number.
Not continuous. As it is binary distribution, ultimately it will return 0 or 1. I mean for each pixel.
I think so. Logit is 28 by 28 continuous number, and this logit is probability to be 1,
Yes.
right?
Yeah.
So we have a 28 by 28 Bernoulli distribution, and we sample from them. Okay, so that's how we get the image.
Yeah.
However, we don't do just one sample. How many samples we do to make a mean?
Except for
We
here
sample,
10.
but that's a prior.
That's the we also passing. Okay, we also actually we are using decoder also here. That means it depends on how many images we are passing to our data. Let's say data.
Likelihood is
Yeah, how many images we are passing to data. So that many samples, that many image samples will be returned from a decoder. Like say from data we are getting code. From code we are finally getting likelihood.
yeah. So make decoder. So What will be the logic? Show me make decoder function. Make decoder function.
Okay.
So, what does the logic mean?
Logic means actually the output of 10 images. That means each image represents 28 by 28 space.
So, what is this 28 by 28 value? What is the meaning of this one value?
I mean, there is no range, I guess. It could be because we are not using any.
I said meaning. Meaning of the logic. My question was meaning.
Okay, I understand.
Mhm.
So it gives you the output of 10 images. That means
So what do you mean by output?
output means the dense layer network output. So the
Yeah.
logic is coming from
Yeah. So, Shadek, let's say we have a 28 by 28 number, right?
yeah.
This is the logic, right? Let's say this is a 0.1, right? What is the meaning of 0.1?
So I don't know what is the. So did you understand?
Yeah, I think the logic is the probability of becoming one. So, and actually it is returning For example, for one image, given one image, it returns a probability distribution of 28 by 28 Bernoulli distribution and given a probability. So let's say if the probability logit is, if let's say if the logit was 0.1, then it has a high chance that the
pixel will be
it will be 0, yeah. And if it is 0.9, it has a high probability it will be a 1, but it does not return the fixed image, it returns the distribution. Okay?
from the distribution. So it's basically taking the mean. Okay. So if you want to get the actual value, we need to take the mean.
That is sample 10, prior to sample 10.
Yeah,
So
but if
prior to sample 10 means, what is the prior to sample 10 means?
prior is basically taking samples
Prior.
with standard deviation.
So we sample 10
Yeah, we are
from
getting
the,
10 samples from make prior.
yeah, and
So then we are passing that to decoder. So from the decoder, it's calculating, it's actually generating the image.
yes,
So you see that there's a difference between make decoder here and make decoder here. So here we need to take the mean to get the absolute value, absolute image samples. But in that case, or here we don't need to take mean. This is a distribution, and this is another distribution is taking log probability. I mean there is no mean here.
so the first one, likelihood is, because this is probability distribution,
Yeah.
okay, Bernoulli distribution. Given the data, we can actually calculate the probability, right?
Yeah.
Because we got the distribution, we know we can calculate the probability.
Yeah.
For the second one,
For the second one, we need to get the actual image value, image data. So that's why we need to take the mean.
yeah, but my question is, will it generate 10 image or 1 image?
In these samples,
Yeah, the
10
samples.
10 images.
10 images?
Yeah. Because we are passing 10 items.
But we also does the mean operation.
Yes. I don't know if the mean is applied for each individual image separately.
There's no access pass, it'll do it overall.
Overall?
If you don't pass an access to the mean function, it will do it for every, it will return a scalar.
You mean given 10 by 20 by 20?
So you mean no.
Ah.
No, it will return image.
So
I will check that. Like say I will write code for sample. Let's say each, like say it is basically for 10 samples. So like say if we pass 10 images, so then we'll generate 10 images from here.
so the output from the make decoder function is actually distribution. right?
Right.
So the mean here is not the like
The normal TensorFlow mean.
It's a-
specific mean for the distribution.
yeah. So in this case, it will be the probability,
Okay.
right? So I think the actual images will be the grayscale image.
Yeah.
Yeah. Yeah, that's why.
MNIST is grayscale.
Amnesty's grayscale, yeah. Yeah. So the samples function will return 10 images.
Yes, so we have two more functions to write.
But why I'm really confused is normally when you do the VAE, the probability distribution is only for the latent vector. But your final output from the decoder should not be a probability distribution, it should be the actual image.
So, if we look at this definition here, so G so this is the decoder.
Okay.
And decoder has a probability of x given z, right? So let's say we have a decoder neural net, right? Given G generates X hat. So let's say it can generate 0.1, 0.9. So there is a two approach here. Two things is possible. One is, okay, given G, we will use this as an actual output, right? That is what you suggested. In that case, you said the probability of what is the probability of X given G is we have original data here, and my question was, hey Shadek, how we can get the P of X given Z, right? And our general consensus was that, hey, this is just a log probability, so we will do X minus X hat, something like this. And my question was, will there be any denominator or things like that, right? However, low probability of X given G. Let's say
there is a reason why we are taking log instead of just taking difference. I mean, there is a, like say, I guess I saw it somewhere. I mean, because of some issue, they are taking log instead of just taking difference. I don't know.
You mean where? Here?
Yeah, like say in this equation, like say why do we need to take log? instead of just taking difference. I don't know exactly remember now. There are some, maybe I need to check it again.
Yeah. Okay. What is Bernoulli distribution?
Bernoulli is
It's probability of being success, which is
0 or 1.
like say head or tail. You are
So the approach taken here. So my question is first here is, hey, are you saying that this squared error is probability? No, right? There are some mathematics missing here,
Yeah.
right? What if we think the output is a Bernoulli distribution and it is returning the probability of being 1, right? It has almost the same thing. So, but because we got the distribution, we can calculate the probability, right? However, probability, let's say probability of being 1 is 0.1, 0.9. But here, the X is MNIST dataset. Who said MNIST dataset is gray? No, I think it should be binary.
Yeah, it's binary.
No, it's crazy.
MNIST
It's
dataset,
binary.
check the.
VAE.
Can anybody check if the MNIST is binary or not?
I mean, I can output scales.
Yeah, it says binary images of handwritten digits.
Mm-hmm. So because X is binary, we have a, let's say, we can say this is let's say if this is 0, so getting the probability of X given G becomes apparent because this is a Bernoulli distribution. So this is mathematically more clean.
Yeah.
And because we sample it from this Bernoulli distribution, there is one more randomness that is possible. So here we have one random. Here we have one more random, which is different from what we know, right? In my understanding, even too, when we have a G, right, not the mu and sigma for G, if we have a G, we get only deterministic image. That was what I was originally thought. But here we have a interesting approach of using distribution one more time and get the mean and generate the gray image, scale image. I'm not sure. So you rewrote the variation autoencoder in the PyTorch, right?
Yeah.
So in PyTorch version of VAE,
We didn't do a second distribution.
yeah, we didn't do
output
the,
that-
yeah, we output the, yeah. So I think this is mathematically more clean, but Paul, can you check in your source code or in PyTorch how you calculate the probability of x given g?
So that's the thing. They don't use
They
the
will use
total
the
loss is the
reduce-
reconstruction loss plus the KL divergence loss. The reconstruction loss they use mean square error.
Mean square.
Yeah.
Okay.
There is no log term there.
Okay. Now. I want you. Hello. Okay. Okay. Thank you. Okay. Pizza is delivered to the
Sherry.
Sherry's office. So, Sanjay, would you please get the pizza?
Series of 6 floor.
Yeah. Ruben, would you please help him and maybe get some cups and trays? Okay. So. I think in theory it should work both ways, right? In theory, I think they look very similar, and there can be some like a local variation, local variant that is not so important. But Paul and Shade, would you please check a few references? For example, some seminar paper about the variation autoencoder, and check which one is how I say original one, which one is a variant. Okay. Yeah. All right.
Then we want to plot codes. Another function to print images. save this plot as an image. Save it.
Shall can you show me purpose function? Okay. Right.
Can you scroll down to the bottom? Just 1 second.
Last one.
Yeah.
They have a trade.
Can you show plot code?
Okay, let's see.
Oh, by the way, I should ask. Can you eat pizza?
I stopped eating pizza for that.
For what?
Generally.
Yeah, so do you have any food you can eat? That can be ordered from the Jim's Pizza?
I will check.
Mm-hmm. when I start.
Look, yes, that's ready. Can you show me plot code?
Correct this spelling mistake. Let's say plot dot samples. It should be plot underscore samples. So the reshape then bracket. Maybe I missed this bracket for feet. After reshape there should be a bracket.
Make template. Make underscore template. Freedom of right.
Error at session 2.
Which is posterior make inside the heel start.
No, what is wrong here?
What do you think is?
It says session.from.
Yes, define it on top. Copy and define it on top. Exactly.
Independent. Turning for you.
Yeah, better than size.
You didn't get this kind of error,
Yeah.
failed precondition error.
Yeah, same.
What is this error?
Can you go to the kernel and kernel? Go to the kernel in the menu
Okay.
and try restart and run all. Restart and run all. Yeah. I think it's okay.
Yeah, that's it.
You too?
Can you send that?
Everybody working?
No, I'm not sure.
Actually, instead of elbow, it should be test elbow. This,
Can you record others?
Yeah.
print test elbow instead of elbow, because elbow is just a placeholder. I mean, node.
Just
Which
line?
Yeah.
This line at the below.
Test album. Print test album. Okay. Oh, because it's doing the.
Yeah, test elbow is the actual output of loss function.
So should I run the last one again?
Yeah.
It's not.
Can you zoom in a bit?
You want to send the code?
Yeah, I think that's it.
So now you get the actual
You make that
cost data.
I'll send it.
As we want to.
Yeah. It's failing in the decoder.
Oh, we got that error again. The failed precondition.
Just do kernel restart.
Oh, okay.
The thing is, when you don't give the tensor's name, it becomes difficult.
Do you have any clue where this error is happening?
In the magma operation side. I'm guessing this is- No, this is called in the whole graph, right? So in the tensor graph, it seems to be failing at the maximum operation.
So you are trying to multiply 2 by 10 and 2 by 200. I have a feeling. So it's a decoder, right?
Actually, initially I thought it was a decoder, but it could be the encoder because it's isn't it failing at the multiplicated phenomenon?
I don't think so.
I'll put this.
So I think are you done?
Yeah, this is now running for 20 episodes.
Can you have other?
Can you just show me the code for make encoder and decoder?
Yeah.
No.
So
I
who is
sent the
still working
code.
on?
I sent the code to them.
Okay.
episodes we have? Iteration 600?
The epochs. We're doing the sample. So it runs for 20 epochs. Right?
Yeah, 20 bucks. So, check the output.
After running for 20
So just go down. You should get that. You should get this one after 90. After the 90th epoch. You should get this. Then it's just a little bit smaller. Check
Can you come on the
the
side?
where you have where you created this, and you should find the image of it.
So you go, it's coming.
So you should find this image in the folder.
Where is the hidden side that you reduce?
So, anyone
It was failing at the other hidden.
was able to create the image, the VAE.png image. So, this is how the image should look like. After 20 epoch, you should be able to see the image. So these are the code on the left bar. So in first epoch, you see there is no cluster of each digit. I mean, they are all randomized. So as we pass, we see the cluster of each individual image. Like say all the images of 0 in one side. Then on the right side, there are 10 samples that has been generated. So as we go down, we see the clearer images. That means the model is learning more, and it was able to generate images. We can actually identify, like say, what each image means. But at the beginning, you see the image is kind of blurry at the beginning of the episodes. But as we train more at the end, the samples are more clear. Like say, you can say this 9. So this 9 or 8, 4, 7, all are created from sampling from random distribution. Like say.
I can't really say.
From here, that means we are just sampling from prior We are not using any input data. So these samples, that's what we are showing in this graph. So it just so these are samples that are passed here. So that's how VAE generate image. Like see, that's why it is called generative model. You can actually generate image without
I'll put log in, I'll see.
without actually training data.
Mm-hmm.